Well, after the proof idea, we come now to just stating in standard format description of a Turing algorithm, or just algorithm. Alright, so this algorithm will decide the language. You can see it, but it's the language big A subscript CFG. Okay, and the members of that language are sort of angular bracket big G, comma W, and big G is a context-free grammar, and that ordered pair G, comma W in angular brackets. It is a member of that language if the big G, the grammar, can derive W, can generate W. Okay? So we will now create the Turing machine. We'll give an algorithm, same thing, that decides that language, and hence we can, with the usual reasoning, chain of reasoning, we can get an answer to the question yes or no whether big G generates string W. Okay, so let the machine that we're creating, constructing, it's a construction proof, call it S, okay? And this Turing machine will decide, well, that's what we're about to prove, it will decide this language, A, CFG, right? As you'd, have I forgotten the double? Yes, I have. I always forget the final double quotes. Here's your, in standard format, the description of a Turing algorithm, Turing machine, same thing. So, as usual, the first thing you talk about is the input string to your Turing machine. Well, it's here's your string that goes in, angular brackets, so it's encoded, representation of the information about two things, the context-free grammar, big G, and the string. Okay, there's two things. So, so G is a context-free grammar, W is a string. Okay, now two main ideas. So the first thing is assuming the formatting of this string is okay, is legal. It passed that test given by the Turing machine. So assuming that's okay, if there are errors in the formatting, then the Turing machine immediately rejects. Okay, and so assuming this is okay. So then you take the information, you know what this grammar is, now convert it so that your, it's easily said, but your Turing machine would have to do that. So it would take this grammar and convert it into an equivalent grammar in Chomsky normal form, CNF. Okay, so you take this G and now you've got a CNF instead, Chomsky normal form grammar. Remember what that is? All the substitution or the rewriting rules in CNF form. They are, the right hand side is either a single terminal or two variables. Right? That's what CNF is. Okay, now since if the string length, now you know the details of the string, so you can easily calculate its length. Okay, so I call that length little n, and you know from previous theory that if your input string length is little n, then you will need 2n minus 1 steps to derive it from your starting variable, big S. Right? Okay, so now calculate all possible derivations of this length. Okay, using your substitution rules. Just systematically generate all possible derivations of that length, and then okay. So there's one exception. If n is 0, the empty string goes in, I guess, then find a list of all derivations in one step. Now, why one step? Well, because you have to have at least one step, because you start with a non-terminal, right? You start with a symbol. Starting state for a CFG is always a terminal, a variable. So you need one step to convert the variable into a terminal. So with like the empty string epsilon, I guess, right? Okay, so you have a look at all these derivations, and if just one of them is w, so if any one of these derivations generates w's, so you're looking at all these derivations, all these the last step will give you a string, a sequence of terminals. So you just check those to see if one of them is equal to w, and if so, accept. You have this machine S, accept, and otherwise reject. So in other words, this machine is accepting or rejecting. In other words, it's not looping. In other words, it is halting. Right? It's making a definite decision. It's deciding, accept or reject. That's what you want. Okay. So we found the Turing machine that accepts or rejects. In other words, it always halts. Therefore, it is a decider, and hence there is a Turing machine that decides each string of the language, and therefore that Turing machine decides the language, and therefore that language is decidable, which is, well, you can't see it, but that's what theorem 4.7 previous session says. A suffix CFG is a decidable language. So we proved it. Alright. Now a bit of commentary, a little bit of blah blah. So determining that whether a grammar generates a particular string, that's very relevant in when you're compiling, for compiler generators and so forth. If you've studied compiler theory, if you're a computer science guy and you've studied theory of compilation, the problem whether a grammar can generate a particular string, so like somebody's using a programming language and types in something silly, then that particular string may not be derivable from the grammar that the compiler is using. So seeing whether a particular grammar can generate a particular string, that's highly relevant in computer science. So this theorem here is highly applicable. Now the actual algorithm for this Turing machine S is awfully inefficient, right? Incredibly, very inefficient, and you'd never use it in practice. Okay, the comment here, but it's easy to describe, and we're not really concerned about your efficiency here. We just want to know if it works or not. Okay. Now, in part 3, the third major portion of the whole text is on, it talks about efficiency of algorithms, effectively. It talks about complexity theory and what that means. That's just a fancy term, effectively meaning how efficiently can you solve problems. Do they require huge amounts of effort by the computer or not? Alright, so if you jump ahead quite a few chapters, go to theorem 7.16, it's on page 266 of your text, and there'll be presented a far more efficient algorithm to recognize a context-free language. Okay? Recognize. Okay. Alright, now another comment, a bit of comments, then we start on the start on the next theorem. The comment here is we proved in chapter 2 there's an equivalence. You can go back and forth between a grammar, context-free grammar, and a PDA. We showed how to do that, so if you want to refresh yourselves, go to page 117 of your text to study up again how you convert grammars to PDAs and vice versa. You can go either way. So in other words, all these sort of questions, computational type questions that we're asking about grammars, CFGs, we can also ask about PDAs, about stack machines, push-down automata, right? Because of the equivalence of these two. So any language that we prove is decidable relating to grammars, well, we can do something equivalent with PDAs. So we don't have to go through all that effort, because these two are just interconvertible. You can go from one to the other, right? So whatever you say about grammars, you can say about PDAs sort of equally. All right. Okay. So then we get to the next theorem. Testing whether a particular, in this case a grammar rather than a machine, recognizes, accepts no strings. Okay, so in this case we're talking about a grammar. So the equivalent problem, computational problem, is there an algorithm that can answer yes or no whether a particular grammar generates no strings? Okay? That's the question. And as usual, convert that computational problem into an belonging to a language problem. Yeah, the same old trick, right? Now here's again, I haven't rectangled it. I'll do that now. Okay. So here's your language. Your input string. Sorry, the members of this language. Of this form. Now there's no W, we don't need it. All we need is the details about the grammar, the context-free grammar. Okay, and this string here belongs to this language if, and here's the conditions of membership of the set, that this G is a context-free grammar, and the language that it generates, is that the word? Yeah, that it generates is the empty set. In other words, it doesn't generate any strings at all. Okay, so we need to find a Turing machine that decides that language, and that'll be theorem 4.8. And here's the theorem statement that this language here is a decidable language. So we're going through this process many times. Each time we just change the language, and the language. Corresponding to the language, there's a corresponding computational problem. In this case, it would be: is there an algorithm that can decide yes or no whether a particular grammar generates no strings? Okay,